We now begin to look at systems of first-order linear differential equations. Now, we already saw what a system of differential equations looked like at the very beginning. So a system of first-order linear differential equations, given in this form, is said to be in normal form. If each f sub I is identically 0, the system is said to be homogeneous. When dealing with systems of equations, it is usually more convenient to write it in matrix form. So we're now going to look at the matrix representation of this system right here. So what we're going to do is we're going to let x be a vector. It's going to be the vector x1 of t, x2 of t, yada yada yada, xn of t. So this is our unknown function vector, or our dependent vector. We'll let a of t be what's known as the coefficient matrix. It is the matrix of all of the coefficients. And then we let f of t be the vector of constants, or of constant functions. It's the vector of all the f's. Then the system can be written in the form x dot is equal to ax plus f. These arrows you should remember from Calculus 3 represents that it is a vector, and a vector is simply a special type of matrix. It's called a column matrix. So if you remember the lesson on matrices, our coefficient matrix is an n by n matrix. The x vector and the f vectors are n by 1 matrices. If we now come back up, look at this system. You should recall that a solution to this system is a set of functions x1 through xn such that when they're plugged into each equation simultaneously, every equation is satisfied simultaneously. Well, since it's more convenient to deal with the matrix representation, we're now going to define what is known as a solution vector. So a solution vector on an interval I is any column matrix. Let's call it capital Phi is equal to Phi1 of t, Phi2 of t, down to Phi(n) of t. So this is the Greek letter capital Phi, and each of these are the Greek letters lowercase phi. Whose entries are differentiable functions of t satisfying the system x dot is equal to ax plus f on the interval I. We now look at matrix form of initial value problems. So we let t naught denote a number in an interval I, and x of t naught, which equals x1 of t naught, x2 of t naught, down to xn of t naught. And we shall represent this gamma 1, gamma 2, down to gamma n, which we call x naught. Where each gamma I is a real number, or a constant. Then the problem given by x equals ax plus f and x of t naught equals x naught is an initial value problem. Remember, shorthanded IVP on the interval. So we now look at two theorems, the existence theorem and the superposition principle. So the existence theorem states, let the entries of the matrices, totally spelled that wrong, A and F be functions on be functions continuous on a common interval. That contains the point T0. Then there exists a unique solution of the initial value problem x dot equals ax plus f such that x of T0 is equal to x0. The superposition principle states that if we have solutions phi1, phi2 through phi(n), of the homogeneous system x dot is equal to ax on an interval then the linear combination given by phi equals c1 phi1 plus c2 phi2 plus yada 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 plus cn phi(n) is also a solution. So superposition principle remains the same. It's just now we're dealing with vectors instead of regular old functions. So we now look at linear independence. So we let phi1, phi2 up through phi(n) be a set of solution vectors of the equation x dot equals ax on some interval I. We say the set is linearly dependent on I if there exists constants C1, C2 through Cn, not all of which are 0, such that C1, Phi1 plus C2, Phi2 plus plus Cn, Phi(n) is equal to the 0 vector for every t in the interval. If the set is not linearly dependent, then it is said to be linearly independent. So we now just need a criterion, and we hope that it's very similar to the criterion studied in higher order differential equations. And in fact, it is. So we let Phi1 be the vector, Phi11, blah, 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 Phi1n, I'm sorry, Phi(n)(1), then Phi2 will be Phi2, Phi12 down to Phi(n)(2), and finally Phi(n) will be the vector Phi1n down to Phi(nn). Then the set is linearly independent on an interval I if and only if W, the Wronskian of them, which is defined as each column of the Wronskian is one of the vectors. So the first column will be Phi1, the second column will be Phi2, and the final will be Phi(n). Equals is not equal to 0 for every t in the interval I. Now, it can be shown that if the Wronskian is not 0 for some point, then it is not 0 at any point. We will not show that. We will just take it for granted. Now, any set of n linearly independent solution vectors on an interval I is said to form a fundamental set of solutions. On the interval. So again, this is just like when we studied higher order differential equations. So the existence theorem for this states that there exists a fundamental set of solutions for the differential equation system x dot equals ax on an interval I. So this theorem guarantees that any system of equations will have a fundamental set of solutions over some interval. We can now form the general solution. We start for the homogeneous system. So given a fundamental solution set, over an interval I, then the general solution on this interval is phi equals C1, phi1 plus C2, phi2 plus yada 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 plus Cn, phi n, where each of the Ci's is an arbitrary constant. If we now look at the general solution for the non-homogeneous system, we let phi p be a given solution of the equation on an interval I, and we let phi c denote the general solution of the corresponding homogeneous equation. Then the general solution is their sum. As before, phi c is called the complementary function, and phi p is the particular solution. Throughout the rest of this topic, we will be looking at how to solve both the general, both the homogeneous and finding a particular solution to solve a non-homogeneous. That concludes this lesson. I hope you've learned something, and we'll see you in the next one.